Okay. Greetings, Algebra Express. You've made it to episode 2 of the lectures. So in this lecture, we're going to cover Merecek, chapter 2.1. The title of this is Use a General Strategy to Solve Linear Equations. This title is a lot better than the chapter 1 title, I'd have to say. We actually do solve stuff in these notes. And before I jump to the notes, you probably see already the first thing that we're talking about is the distributive property. There's two other properties I want to talk about before I even get to the distributive property. And if I write them out, you'll probably notice them. If I do something like this, and so if the letters confuse you, you can throw numbers in there. So like what, 2 times 3 times 4 is going to be 2 times 3 times 4. And so what this tells me is it doesn't really matter a whole lot with how I group things. You can do this with multiplication. This property also works with addition. 2 plus 3 plus 4. I'm using the same numbers. I don't have to use the same numbers that I did previously for the multiplication. I'm just being a bit lazy maybe. My camera's lagging a little bit, seems like. There we go. Okay, so this tells us it doesn't matter how we group things. When we multiply and add, this property comes up. And so it doesn't matter how they're grouping each other. If you think about how you group with other people in life, that's the way I want to say it. If you think about how you group with other people in life, that's how you're associating with other people. And so this is like sort of like the numbers who's associating with who, right? Is the 2 associating with the 3 first and then the 4 is coming out? Or is the 3 associating with the 4 and then we're going to throw the 2 back in there, right? And so I'm hoping you've seen this property. If you want to do this, you can multiply things through 6 and then multiply it by 4. That's going to give us 24. We do 3 times 4. That's going to give us 12. Multiply it by 2. That's going to do 24. So if you don't see these properties, or they're not super obviously like readily like or if they're not readily obvious to you, I guess is what I'm trying to say. If they're not readily obvious that these are things and that these are true statements, you might want to do a little bit of number crunching and prove it to yourself, right? Add the 2 and the 3 and then add the 4 and then try it the other way around. And so this is the associative property, as I've already said. And so this is one property. Another property, and I'm going to use less letters this time, is this sort of thing that says if we do A times B, that's the same as B times A. So pick 2 numbers. 8 times 7 is going to be the same thing as if you do 7 times 8. I could have threw more numbers in here, but basically this thing is kind of telling us, and you can do this with addition as well. 5 plus 4 should be 4 plus 5, right? It doesn't matter. This thing is basically telling us it doesn't matter what order, right, we write things in if we're adding and multiplying. And so addition and multiplication, we're going to say the order that things arrive to the problem doesn't matter. And so if you think about the order that or the way that you arrive somewhere, that would be like your commute. And so it doesn't matter how these things commute to the problem. They're still going to give you the same solution, right? We're still going to get the same numbers, whether we multiply 8 times 7 or 7 times 8. So this is called the commutative property. And as I said, we're using these with respect to math, but in general, I think I maybe have said it, but math can be kind of thought as an application of set theory. And so if we're thinking about like sets of things and objects, like that pretty much pertains to everything that's out there in the world. And so we can actually think about these things and things that aren't math as well, right? Other things like what, putting on your shoes and socks. We're going to ask, is that a commutative operation? Does it matter what order you put your shoes on and socks on, right? It obviously does. If you put your shoes on first and then you put your socks on over your shoes, it's going to look kind of weird. So things like putting on your socks and shoes are a commutative operation. See, we got to think about math with everything, right? Something you probably never wanted to do, but here we are. It does help you out. It really helps you structure your thought, is what I would say. So we have something like the associative property. It doesn't matter how we sort of group things if we're doing addition and multiplication. And we got the commutative property. And so I didn't really say this, but multiplication is commutative. If we think about division, divided by 7 is not going to be 7 divided by 8. So things like division, things like subtraction, we say are not commutative. Things like division and subtraction are not necessarily associative, right? Okay, and just to review, like these are sort of like properties that are going to come up again and again. That's why I'm kind of throwing them out there. It's just to get you sort of familiar with this. Associative is how the numbers associate with each other. Commutative is how they like arrive to the problem, right? And so we'll definitely see these come up again and again. Like I'm not expecting maybe to like to have everything just memorized in one night, right? Okay, and so a little bit about distributive. If we look at the distributive property, I think most of you are probably somewhat familiar, but if you need to, we can kind of look at it like A gets multiplied to B and A gets multiplied to C. So sometimes people like to draw on the arrows to kind of indicate what's happening. And I think if we just jump into this sort of first thing, so I think one of the things that might mess people up is just the like standard math notation that we're all used to, well, I say we, mathematicians are used to using, right? And so if we have to fill in things, it might help. If we have to fill in a coefficient, this is like a 1t happening here, right? If we have to fill in powers, if it's t, it's always like t to the first power. And so if we're doing this, if we're doing the distribution, if we do minus 6t, the first thing we have to multiply it by is t, and then the next thing is this minus 2. So we're taking a minus 6t, and the first thing I'm multiplying it by is a 1t. And I also have another minus 6t. And the next thing I'm multiplying it by is this minus 2 here. And now I'm looking at this problem. So I have a minus 6t times a 1t. And so we're actually going to make use of those two properties I was talking about. So I think a lot of people sort of just use those properties without realizing they're kind of using those properties. But what I'm actually going to do is I'm actually going to rearrange the minus 6 times the 1. And I'm going to look at that like as kind of like a t times a t. And so you probably just look at minus 6t, and you probably look at 1t, and you could probably like right away tell me the minus 6 times the 1 gives you a minus 6. And the t times the t is going to give you the t squared. We're doing a sort of similar thing over here. We're doing a minus 6 times a minus 2, and then we're tacking on the t at the end, sort of. And so this 2 negatives should give you plus 12t. And so I really don't expect you to write this step out, to be honest. You could probably look at this step and kind of do it. You could probably even look at this first step and probably kind of jump down to here. Hopefully you've had a little bit of experience with the distributive property before this class. so let me make sure I get all that on there. I think that about covers that problem. Okay, so let's go on to the next one. If we look at this thing, we have a negative on the outside, we have an x, we have a minus 3z. And so if you have to, and I think I did this in the previous notes, if you have to write a number here, this is going to be sort of like a minus 1. And so we can multiply minus 1 by both of these entries here. And if we do that, this is a positive 1x. A positive 1 and a negative 1 is going to give me a negative 1x. And now we have a minus 1 and a minus 3z. So minus 1 times the minus 3 is going to give me a positive 3. And there's still a z attached. If you came to this, this is fine. Although personally, if I was doing this, I would probably carry it just like one little step further. We typically don't write the 1 if it's there. And so we filled in the 1s. Now I guess we need to take away some of the 1s. Minus x plus 3z. Okay. And so let's go on to part C. And so this one, I think, brings up probably like an interesting concept. So if we have, because this is kind of going back to the order of operations from chapter 1. If we have these things, the first thing we're supposed to do is those parentheses. Obviously, we have a 2 minus x. And I hadn't really talked about this a whole lot. But this is a 2 with no x's. This is an x with a single x. And so when we're adding and subtracting, what we look for is like terms. And these are not like terms because this has an x and this has no x's, right? And so if we look in the parentheses, there's not a lot we can do because these things are not like terms. But we can do a little something with that property we just learned. So we can do the distributive property with this. If you have to, this is a minus in front of a parentheses. You can always put that negative 1 out there if you have to. And if we do that, now we're distributing a negative to everything that's in the parentheses. So this should look like 5 minus 2, and this minus x should then become a plus x. And so now we can do a little bit of cleaning. Now there are like terms that we can combine. We can combine the 5 minus 2 to a 3 and get something like 3 plus x. Okay, and so that is part C. So let's look at part D. So now they're just making it maybe a little more complicated by giving a few fractions. Okay, it's still the same distributive property, still the same process. So we're multiplying this 8 by 7/8. We're multiplying 8 by 3/4. And so the first thing I see is 8 times, and maybe I'm writing this a little weird, 7/8. And there's a y attached to this. And I'm going to, and you can do this different ways, but I have to account for the negative. And I have to do 8 times 3/4. And now we're multiplying fractions, and going back to the first chapter notes, we do numerator times numerator. We do denominator times denominator. I just see an 8. I don't see a separate numerator and denominator here. So what can I do to a whole number? Well, if you divide something by 1, it's still going to be itself. 8 times 1 will get me back to 8. 8 divided by 1 will be 8. And so this is still the same number. So if you have a whole number, there's kind of like it's understood you can always divide it by 1. And so now I'm at this step. And there are a few different ways you can do this at this point. And so I think I'm going to go through probably at least 2 different ways to do this. So one way is you can just do it kind of brute force. You can do 8 times 7 will give you, what, 56 over 8. And this is y minus. And we can do 3 times 8 is going to give me 24 over 4. This is probably like the most forward way. If you're following from my instructions from like the last chapter, this is probably like the more obvious sort of way to go about this. Doing this brute force, right? And this is a valid way to do it. 56 divided by 8 will give you 7y. Minus 24 divided by 4 will give you 6. That's absolutely a good way to do it. Now let me show you. Take 2. What's another way we can do this? So there is a sort of way. Come back up to this step. There is a sort of way to simplify these things. And you can cross-simplify is the way that you go about it. So let me grab this. Here we go. Got my red pen. Okay, so let's look at this. If we go crossway, there's an 8 here, there's an 8 here. So if we divide 8 by 8, that's going to give me 1. If I divide 8 by 8, that's going to give me 1. Here we're going crossways. I have a 4 here, I have an 8 here. So the common factor these both have is the 4. If I divide this by 4, it's going to give me 1. If I divide this by 4, it's going to give me 2. And now if we look here, I think we have nothing but 1s on bottom. So we have 7 times 1 on top. So I have 7 over 1 should give me, can I get all, I have to zoom out a little bit. All right, let's see if I can get it all on here. There we go. And so if we look here, I'm hoping you notice this is 7 over 1 is going to give you the 7. This is going to give me 2 times 3 on top is 6, and I only have 1 on bottom is where I'm getting this 6 from. So if you know how to simplify these things, cross-simplify, that's absolutely a better way to go about it. Go for it, is what I'm telling you. Okay. It's really tempting to ask if there's any questions, but I think answering those questions, asking those questions might be a bit difficult for y'all. Okay, so we did number 1. We practiced the distributive property. And so now we're going to practice things with multiple distributive. And so we have something like 5 times x minus 2 plus 4 times x plus 3. And so I want to go a little bit faster on the distribution step. So we've done a few examples. I'm distributing this here. I'm distributing this here. So 5 times x minus 2 to get out of that is 5x. 5 times a minus 2 would be getting 8. And now the next thing I have is a plus 4 times x is going to give me plus 4x. And plus 4 times 3 will give me a plus 12. And now this is going back to that property I mentioned at the beginning of the notes. We're actually employing the, I believe, commutative. We're going to rearrange things in this problem. It's all addition and subtraction. So you can look at subtraction as being adding a negative. And so maybe that's kind of a weird thing. We are still technically employing the associative property, right? And so as long as we account for the negative on the number, it is still technically addition. So maybe that's a weird thing to do, but it is still technically the associative property. So if we have something like 5x plus 4x, I believe that's going to give us a total of 9x's. And if we have a minus 10 and a plus 12, I believe that's going to give us something like plus 2. And there's a similar thing happening in part 3. First thing we're distributing, we got to distribute the 3 to the 4x. We got to distribute the 3 to the negative y. And this is that thing. If you want to put your 1 here, you can put your 1 here. I think I'm going to start maybe dropping the 1 and just throwing this here. You can think of it as just it's a sign swap. If it's positive, it becomes negative. If it's negative, it becomes positive, right? Okay, so 3 times 4x, that's going to give me 12x. And if I do 3 times a negative y, that's going to give me minus 3y. And now I'm distributing this negative. So I distribute the negative. I have a minus 2x. And I have a minus 3y. Now I'm looking along here for like terms. And so I can only add apples to apples, bananas to bananas. I can only add x's to x's. I can only add y's to y's. They are talking about different things. You can only add terms that are alike. So if I do 12x minus 2x, that is going to give me 10x's. If I do minus 3y and another minus 3y, that's going to give me minus 6y's. Whew. And so that is the first page. And so we have not actually solved anything yet. We have simplified, we've used the distributive property, we've done all this stuff, and they're doing this stuff for a reason. They're doing this stuff to set you up to solve stuff. So don't feel like it's in total vain. They're leading to something on these notes. They usually do. And that's exactly where we're kind of going with this page. So now they're talking about solving basic equations. So now we're solving first order linear equations. And so the first thing they talk about when solving is use the distributive property. So if you have parentheses, none of these first 3 do, but they will on the next page. So if we have parentheses, we need to get rid of the parentheses. And then we can use something called the addition principle or the multiplication principle. So you could read their definition there. I think I'm just probably going to jump into the problem and like highlight what they're talking about with the addition principle, with the multiplication principle. Because I feel like it's a fairly straightforward thing if you just see it in the problem and you use it all the time without even realizing you're using it probably. Before I get to that, though, I want to ask an important question. What is it? I want you to think about this question. Like, what does it mean to solve something in math? What does it mean when we get a solution? What does that solution look like? What does it do? Like, what is its purpose? Huh. Okay. So if I ask you to solve this, I'll come back to that in a second. What is the solution? If I ask you to solve this, I feel like most of you could probably do this before you even started this class. If I ask you to solve this, I want to get x by itself. So if I ask you to find a solution, we want to get the x single and by itself, right? So that's one way you might start defining a solution. We got to get the variable single and by itself. Okay. So we got to get a value for the variable. So we got to get the x by itself. It's attached through multiplication to this 2. Further out, I look further out, it's got a minus 5. And so I look furthest out and I kind of work this thing backwards. And so if I want to get rid of a minus 5, I have to add 5. And this is that addition principle that they're talking about right up there. It says if we have something that is equal, we can add the same number to both sides of that equation. And this thing will remain equal. This thing will remain true that it's equal, right? So that's what the addition principle. principle says. We can add or subtract a number to both sides. Now we have 2x equals 1. Ooh, don't know how to add. 5 plus 1 is 6. Sorry. Let me repeat that. If we look at the left side, we have 2x minus 5. If we add 5, we're going to get plus 0. It's only going to give us the 2x. 1 plus 5 is going to give you 6. And so now we have something like 2x equals 6. What's the next thing? This is multiplying. If we want to do the opposite of multiplying, we can do division. So I guess you could multiply by a half, would be the same thing, but we're dividing by 2. And so this is the, probably guess it, but this is the multiplication principle that they're talking about up there. And so we can multiply or divide by the same number. And if we do that, this is going to give me what? X equals 3. It's going to give me my solution. Okay. And so I want to go back to this, like, what is a solution? And so we get the variable single and by itself. But if I'm talking about the solution x equals 3, what does this mean with respect to the original equation that they gave me? So if I'm looking at x equals 3, what does it mean? So I can take this x equals 3, I can take it, I can do 2 times 3 minus 5. And what is that? What is this? This is something that is always going to be true, right? 6 minus 5 is 1. So this is a true statement. So in essence, what we're looking for in math is that we're searching for a certain truth. And so we're seeking truth is what we're doing. And that's the way that I would look at a solution. It is something that makes the original statement true. So it is a value for the variable. Or it could be multiple values. That make the original equation true. Keyword here being it's going to make it true. And so I kind of said in class earlier, I know like a lot of you are not going to be math majors, and like I'll have to swallow that, I guess. I'll have to take it for what it is, I guess. But I hope even if you're not going to go major in math, I hope you like start thinking a little bit more like a mathematician, right? And I think that this is probably going to get at the point a little bit. I'm going to talk a little bit about what like sort of mathematical truth is, right? And so there's a really cliche example I'm going to use. So if I say all men are mortal, and if you take a philosophy class, this would probably be in your philosophy 101 or something. If we have that all men are mortal and we know that Socrates is a man, then there's a conclusion that we can draw. And so we're drawing a sort of conclusion from this, and this happens in math, and this is all mathematicians do basically, but we apply it to numbers. And so if Socrates is a man and all men are mortal, then we can draw the conclusion that Socrates would also have to be mortal. And so there's a way that these sort of concepts piece together that make this statement true, right? And it's a truth that like it really doesn't matter about reality. I can start saying like absurd things. I can say all men are, and I can change this word to green, right? And there's something within the construct of our language, within our the way that we word things and the way that sets exist, that makes this thing necessarily true based on these two things. And sort of that, like, that's what we're doing in math. We're creating this truth that exists, and it's a sort of truth, deductive truth is what this is. This is deductive logic happening here. We're deducing things from things that we already know. And it's kind of, the accuracy is kind of based on the accuracy of your knowledge, right? If we say absurd things like green, we're going to come up with an absurd conclusion. But this is true. If all men are green, I guarantee you Socrates will be green as well, right? It's within the construct of our language. And it's something, it's a truth that is very powerful, right? And so there's this thing called mathematical truth that is analogous to deductive truth, right? And it's kind of a weird thing. We can say absurd things in math and be crazy. Okay. So I think the next thing, that was a little bit of a tangent. So going back to what we're talking about truth and sort of like what that means. So a solution is something that gives you a true statement. So I didn't box my solution, but you probably want to box your solution even if you do some checking. So I can see where your solution is. It's always a good idea. And so now on the next one, I have a negative 3/5 p equals 6. And so if I'm looking at this, what I want to end up with is something that looks like 1p to the first. If I get it single and by itself, that's what I want. It's already to the first power, so maybe you can ignore this exponent here. But we need to get that 1 in front of there. And so how do we do that? Well, this is 3/5. Well, there's a fancy word for what you multiply to get to 1. The fancy word is called reciprocal. All we do is we flip this thing. So if I want to go from 3/5, I got to multiply it by 5/3. And we can do this in 2 steps if you really want. But I think I'm going to do it with 1. If this is a negative and I want it to end up being positive, go ahead and tack a negative on there. So minus 3/5 p is equal to 6. And so since I multiplied that side by a minus 5/3, I also want to multiply this thing by a minus 5/3. Okay, so let's look at the left side. Negative times negative is going to give me the positive. 5/3 times 3/5 is going to give me 15/15. That's going to be 1. So that's going to give me my 1. It's a reciprocal. It should work out. The right side, I see a same thing sort of happening again that happened in previous problems. I have a whole number times a fraction. So if you need to do it, go ahead and write this thing over 1. And so now I'm calculating this. I'm going to use the shortcut that I talked about previously. So if I have 6/1 and 5/3, I have a 3 and a 6 here I can do some simplifying with. And so I can divide both of these by 3. This would be 1, this would be 2. Negative times a positive, so my solution should be negative. I have a 2 times a 5 on top is going to give me 10. I have 1 and 1 on bottom. I don't have anything left on bottom. So p equals a minus 10 should be your solution. If we want, we can always check our solution. So a solution is something that makes the original statement true. So if we want to check the solution, we have a minus 3/5. We want to multiply that by a minus 10, that equals to 6. We're going to do that same sort of trick, put that over 1. We can simplify this as 1, we can simplify this as 2. And so a minus 3 and a minus 2 is going to be a positive 6. And so we should end up with a true statement. If you carry it, you should end up with some sort of identity statement, if it is a solution. I know I didn't carry this first one all the way, huh? I could have carried this 1 to 1 equals 1 if I wanted to. Okay. T divided by 3 equals a -1. And so how do we solve this? If t is being divided by 3, so the opposite of dividing would be to multiply. So instead of dividing by 3, if we multiply by 3 to both sides, you might have that same sort of problem. We have to do 3 over 1. We're going to get 3t over 3. That's going to give me t on that side. We could simplify it if you want. So this is 1 and this is 1. And the left side is going to give me t. The right side is going to give me a -1 times 3. It should give me a -3. Again, we can go plug this in. We can check our solution. -3 over 3, is that a -1? And if I carry it all the way, I should get something that looks like the identity, or a number is equal to itself, right? We call this thing the identity. Okay. And so these are equations, and they're basically an expression equal to a single number, right? An expression equal to a single number. And so these were sort of like basic equations, so we could get a little bit of practice on the addition principle, on the multiplication principle, and doing like the inverse operation, right? And so now they're going to give you something. They're going to up the notch just a little bit, and they're going to do equations with variables on both sides. And so now we got numbers and letters on both sides. And so in general, if we want to solve an equation, you typically get everything with the variable to one side and everything without the variable to the other. And so we want to get all our x's to one side. We want to get all our constants to the other. There's a few ways you can do this. And so let's start on number 4. And so we start on number 4. I look at 2.3x minus 6.4 equals 7.1 plus 12.8. So as I said, there's a few ways you can do this. You might be doing it differently from the way that I'm doing it. And that's perfectly fine. You should still get the same solution. And so I'm looking at this thing. These aren't the prettiest numbers. They are giving you decimals in there. But we can still work with it. You should have, worst case scenario, if it's really tripping you up, you should have a calculator, right? Okay, so let's move the 7.1 first. I think that's what I want to do. So if I want to move that 7.1 x, it is a positive 7.1x. I want to use the addition principle. And so I want to subtract 7.1x from that side. If I do it from that side, I have to do it from the other. And so now I'm trying to do 2.3 minus 7.1. Those are not the prettiest numbers, but we can do it. It should give you a negative number because the larger number is negative, and it should give you a minus 4.8x. And I have minus 6.4. And this is equal to 12.8. And so I've moved all my x's to the left side. And if my variables are on the left side, I should put things without my variable to the other side. So from this point, if you did that step, there's really one thing you should be doing at this point, I think. And the next step should be to add 6 points. And if I'm looking at this, this is giving me what? Minus 4.8x. That's giving me the 0 I want. If I add 12.8 and 6.4, that should give me 19.2. And so these aren't the prettiest numbers, but we can do it. It's doable. And hopefully you'll have a calculator. If it's really tripping you up, you can use that thing. Okay, so now we're doing what? Minus 4.x is 19.2. So the operation between the x and the 4.8 is multiplication. So if we want to get rid of this thing, the next step we should be doing is dividing by 4.8. And if we want to make it positive, it should really be a negative 4.8. So we divide both sides by a negative 4.8. The same number over itself is going to be 1. So I have my 1x here that I want. Now I'm probably pulling out my calculator to do this, but it's not too difficult. What is it? 4 times 4 give you 16, times 8 will give you 32. I believe that's it. So I believe this is an even 4 that this divides out into. Again, if we want to check this thing, we could go plug it back in place of x. We would have to plug it in here, and we would have to plug it in here. So we'd have to plug it in 2 spots in this one. But it should give us a true statement. And again, you probably have a calculator, so it does look kind of nasty, but if you're going to plug in a number, it's not really going to take you too long to crunch that on a calculator. To check your answer, it's a good way to check. Okay, so the next thing, y minus 3 times y plus 2 equals 2 times y minus 7. Oh, this is a bit different from anything we've had so far. And it's a bit different because it has a few more, it has parentheses. I don't even believe, no, the previous ones didn't even have any parentheses. So this is the first one with parentheses and numbers outside the parentheses. And I'm hoping you're like itching, like you're like, hurry up with it, just say the number. We're doing this distributive property here, right? Okay, so let's do some distribution. We got to distribute that there. We got to distribute that there. So the first thing I see here, the first thing I'm laying down is a y. I'm doing minus 3 times y is going to give me minus 3y. I'm doing minus 3 times 2 is going to give me minus 6. This is equal to, I'm doing 2 times y is going to give me 2y. I'm doing 2 times and minus 7 is going to give me minus 14. And so it's a little bit more involved. It's prettier numbers than the previous one, but maybe it's a little more involved with the steps. So let's look at what to do next. If we're looking at this, typically I want to remove everything with the variable to one side, everything without to the other. But if I just did some distribution, one thing you can kind of check that might make things easier, and if I have to put a 1 here, I can always put my 1y in front of the y. Are there any like terms that we can combine? And so if I look at this, I'm doing what? 1 minus 3. So 1 minus 3y is going to give me a minus 2y. And I have a minus 6 that I'm still bringing down. And I have a 2y minus 14. Okay. Let's not move up too quick. Okay, so we have a minus 2y minus 6 equals a 2y minus 14. And so now how are we solving this thing? Still the same strategy that I said before. Everything with the variable to one side, everything without to the other. So I think I'm going to do this backwards of what I typically do. I think I'm going to move my y's to the right side. Just to have things a little bit different. And so if I do that, this left side then becomes minus 6. This becomes 2y plus 2y becomes 4y. And I still have a minus 14 there. And so now I'm looking at this, minus 6 equals 4y minus 14. I want to get my y by itself. And so if I want to get the y by itself, there's really one sort of thing I should be doing if I get to this step. And that's moving this 14 over. So if I add 14, Minus 6 plus 14 is going to give me what? 8. 4y, and if 4y equals 8, we can divide both sides by 4, and we can get 2 equals y. Okay. And if I want to check it, I can check this thing, right? I can plug 2 in. There's going to be 3 places I plug 2 in. I can do 2 minus 3 times 2 plus 2 times 2. And so now I'm doing order of operations. 2 minus 3 4, 2 minus 5, 2 minus 12. Is that equal to a minus 10? I believe so. Okay. And so I kind of did it. There's one thing that people might mess up on this that I just kind of thought about. So when I did this and I did the distribution, you might notice the minus 3 is the thing that gets distributed to the y plus 2. So I want to make sure we're not seeing this thing as a foiling problem, right? If it was foiling, there would be parentheses around the y minus. And so this is not saying that. This is not telling you to do y minus 3 times y plus 2. So I just want to make sure that we know that those are different problems, right? Have a visual cue. That is not the same. Okay. So make sure you're only distributing the thing that's right outside of the parentheses. We're not going back to this thing unless we're grouping this thing with parentheses as well, right? Okay, next thing, we're going to do equations with fractions now. So previously we had to find LCDs. We had to convert everything to the LCDs. And so if you want to do that thing like we were doing in chapter 1, that will get you there. And I've seen students work it that way. But personally, there is an easier way to get rid of fractions. So we still have to find the LCD. LCD between 2 and 3. I don't want to spend a whole lot of time on it, but it's 6. And so if I know my LCD, there's a bit of a trick I can do. I can take this side, and I can take this side, and I can multiply both sides by the number 6. And so if I multiply both sides by the LCD, I'm going to have to do some distributing. So the left side looks like 6 times 1/2 x, and I have a minus 6 times 2/3. And this is equal to minus 2 times 6. I can write that out already. That's minus 12. Now we're back to that thing of I have whole numbers and I really want to multiply by fractions. So if I have to, I can do my 6 over 1. I can do my 6 over 1. And so I'm probably going to do this a little quick, but this is 6. And then I'm going to end up dividing it by 2. It's going to give me, and there's an x attached here. I'm going to do 6 times 2, which is 12. And then I'm going to divide it by 3. It's going to give me 4. And this is equal to minus 12. If you want to do the simplification, you can do the simplification. And it'll give you the same solution. 1 and 2. And so now I have something that looks like 3x minus 4 equals a minus 12. I'm hoping this looks a lot easier than that first thing they gave you with the fractions. And so now we're going to add 4. And we get something like 3x is a negative 8. And now the next step, we want to solve x. X is a minus 8/3. All right, same thing with part 7. So in problem 7, we have 5, 6x equals 2/3 minus x. The first thing we want to do is the LCD of 3 and 6. So if we're looking at the least common multiple of 3 and 6, it's going to be 6. So we multiply both sides by 6. So we have 6 times 5, 6x. And we also have 2/3 minus x times 6. And maybe I wrote this a little weird. We're distributing that 6 to both of those terms in there. So I know I'm changing the orientation or the side that I'm writing on the parentheses, but it should be the same either way. And so if I'm looking at this, you might want to do it like over 1. And if you look at that, then we can do some cross simplifying. This side should give me 5x. And if I'm looking at this, this gives me 6 over 1 times 2 minus 6 times x, and gives me minus 6x. And so it's still a little bit of simplifying. 6 times 2 is going to give me what? 12 divided by 3 will give me 4. Minus 6x is equal to what? 5x on this side. We have variables. We have constants and variables. So it looks like the easiest way is probably to move my variable over to this side. If I want to do that, I have to add 6x. And so I'm getting something like 11x equals 4. Let me write it. Okay, 11x equals 4. And if I want to solve for my x, the last thing I'm doing is dividing. Almost there. X equals 4/11. And that's your solution. Oh man, that's our solution. If I really wanted you to hate me, I'd make you check that by hand. That is not a pretty thing to check by hand, right? 5, 6 times 4/11, 2/3 minus 4/11. Woo! If you have a calculator, it's probably not too difficult. But okay. So that's the last problem on page 3. We're almost done. We have 2 more problems. I'm going to ignore what they say. So I talked a little bit about what the identity property was. We know what it means to contradict something. Unconditional. So I talked a little bit about solutions. You might notice this is a student activity, so typically in the physical class, make them wade their way out through this and make them do it on their own. But we want to think about, like, what is a solution? And I talked about it earlier, where it's that search for truth, right? And so we're looking for truth. We're looking for values of the variable that make things true. And so if I'm looking at this thing, looks like 2x minus 5 equals x minus 10 minus x. I have to do some distributing. So let's do some distributing. 2x minus 10 equals x. We do minus 10, and it's a plus x now. Okay. So I did some distributing. Now after I do some distributing, I can combine these two things. So there's two x's over here. And so now I'm going to that strategy of how do I solve things. I get variables to one side, I get constants to the other. Okay, so let's try to move our variable first. And so if we want to move the variable, what we're going to have to do is something like subtracting 2x. And if we do that, this is 2x minus 2x. That's going to give us no more x's. There's 0 x's. So if I wanted to, I guess I could say 0x minus 10. I really don't need to write the 0x. If I wanted to, I could write the 0x minus 10. I really don't need to write that 0x. This is just saying minus 10 equals minus 10. So what is this telling me? If I want to, I could add 10 to both sides. And I get like these Jeep headlight looking things, right? What is this telling me? I tried to solve for a variable, and there's like some weird stuff happened. This variable kind of disappears out of the equation, right? And I get something that looks like 0 equals 0. And so maybe you want to notice this is like the identity thing that we were getting to earlier. And so an identity, the number is equal to itself, but more importantly, this is always, 0 is always going to be 0. 2x minus 10 is always going to be 2x minus 10. So what is that telling me with respect to the solution? Well, it doesn't really matter what I plug in. This is always going to be true. So I can plug in any and all real number out there, basically, right? If I do 2 times any real number that we know of, and I subtract 10, it's going to be equal to that same number times 2 minus 10. This property is going to be true of any real numbers. And this is going to be true of any x that we plug in. So maybe another way to say it is plug in x to this equation. Okay, I've already done that. There's no more x's there. And this is always true. And so this is all real numbers. Right, with the pound sign. All real numbers, all real numbers. Or this thing called script R. Not drawing it the best time. A little bit. It looks like an R with an extra little line on it. And so we can plug in any number that we know of out there, and this will always be true. It'll always be true that 0 equals 0. It'll always be true that minus 10 equals 10. And even if we go plug in the number anywhere, right? As long as we plug in the same number, any real number will make this true. Any real number will make this true. You can try it. I'm not going to try all the real numbers out there, so it's up to you. Okay. Next thing looks like 5 times 3 minus x equals 8 minus 5x. I'm hoping that the first thing you see is parentheses. The first thing in your mind is like distribution, right? So we gotta do some distribution. So if you distribute the 5, it ends up with something like what? 15 minus 5x. 8 minus 5x. And now this looks almost similar to the one above. So in order to get rid of the variable, in order to move the variable, we have to add 5x to each side. If we add 5x to each side, we get something like 15. So now I want to ask the same question. What values of x can we plug into this that will make this true? When will 15 be 8? Is there any number that if we take 15 and we subtract 5 times that number, will it be the same as 8 minus 5 times that number? And so this is always false. If you want to contradict someone, You're saying something that's always contrary to what they're saying. You're saying that something to make what they're saying false, right? And so this is known as a contradiction. A contradiction is a statement that's always false. It's gonna have absolutely nothing we can plug into it that will make it true. So we can say no solution. We can say empty set. The empty set looks like a circle with the line through it, right? Or no set is also what it's called. A little big. Goes just a little past the circle. Okay. Okay. So just to kind of recap, we talked about solutions, right? And when we talked about solutions, let me grab a paper from here. We could get these solutions on things that look like single variable solutions, like y equals 2 or x equals 4 if I flip this thing around, right? We get these solutions that look like single numbers. Those are one way that solutions could look. That is known as conditional equation. These things are conditionally true. They are true when x is a specific number. So that is one way. That is the most common way that we're going to have when we solve things. And so most of the time, they're going to be conditionally true. They're going to be conditional equations. Occasionally, we will have an identity or a contradiction, right? And to recap this, if we have an identity, something that looks like 0 equals 0, right? That is something that is going to be always true. And so it didn't really matter like what number we plugged in. This was just a property that they gave us that was the same thing over again, right? And somehow the x would simplify out and it would give us something that's always true. It doesn't matter what number we plug in there. So this is a special case sort of thing that might happen. The other way was a contradiction, right? And so there's a possibility that doesn't matter what we plug in, nothing we plug in is ever going to solve this equation. There's no way to solve that equation. It's always going to end up with some kind of contradictory statement, right? And so I want to be sure the null set does not mean 0, right? You can have a solution that is 0. And let's give an example maybe. So we have like something 15 plus 4x. 15 plus 4x and 15 plus 5x. I want to move all the variables to one side. I'm going to subtract 4x. Like something like 15 is equal to what? 15 plus 1x. I could subtract 15. I'll end up with something like 0 is equal to 1x. And so this is giving me the x equals 0 equation, right? And if I want to go back to what a solution is a number that makes the original statement correct. So if I do 15 plus 4 times 0, and I do 15 plus 5 times 0, you might notice I do 15 equals 15. This is a valid solution for that. So 0 can actually be a solution in itself. Really? Do you want to complete this? Yeah. Okay. Next time. It'll be conducted by Willy Wonka. Y'all heard him. Okay, so back to this. We can have a 0 solution for this thing, right? Absolutely. The 0 works for this equation. Let's go back to this thing just to show you, does it work for this? Could we plug in 0 here? Would it work? 5 times 3 minus 0, just to show you it's not going to work, right? Equals 8 minus 5 times 0. I believe this is giving me 5 times 3 gives me 15. This gives me 8 on this side. So it definitely does not work if I plug in 0. I get something that looks very similar to that contradiction up there, actually. Okay. Well, I think I probably went above and beyond on these. We did the notes and then some extra, I think. So I think that should conclude this session. I hope to see you in class tomorrow. Come prepared to ask questions, all right? See y'all, and we'll work through some homework tomorrow. Thank you.